Hello everyone. In this video is presented a poster titled Synthesis and Characterization of Strontium-2 Iron Molybdenum 1-X Niobium X Oxygen 6 double perovskite compounds. Perovskite-type compounds are very interesting due to their diverse properties, such as magnetism, spin polarization, optics, mixed electronic ionic conductors, and others. In particular, the strontium-2 iron molybdenum oxygen 6 compound exhibits a transition from a half metal ferromagnetic to an antiferromagnetic and semiconductor behavior when molybdenum is completely replaced by niobium. Therefore, this study will examine the influence of introducing niobium and the molybdenum sites, looking for the modulation of these properties. Results and discussion. The compounds were synthesized by solid-state method in an hydrogen atmosphere with X equal to 0.5, 0.6, 0.7, 0.8, and 1.0. Figure 1 shows that the compounds were obtained in a pure phase. A shift of the main peak to lower angles is also identified. This indicates an increase in the lattice parameters, and this confirms that we have the introduction of niobium at the molybdenum sites. The crystal structure was studied through the Rydberg refinement method performed on the diffractograms. The reflection peak 101 is associated with the ordering of the iron and molybdenum cations. This peak decreases as the niobium content increases, indicating a higher content of anti-side effects and therefore the disorder increase. So a phase transition from tetragonal I4M to IMCM is identified for X greater than 0.7. Figure 2 shows that the XPS survey don't show unexpected elements. High-resolution spectra indicate that in all the compounds with molybdenum, there is a mixture of molybdenum 5+, 6+, which tends to be mostly molybdenum 5+ as the niobium content increases. This is due to the charge balance, while niobium always remains as niobium 5+. Valence band studies in the figure 3 indicates a decrease in intensity at the Fermi level as the niobium content increases in the compound. This indicates a lower conductivity of the compound. On the other hand, magnetic measurements show a greater saturation magnetization when there is a higher molybdenum content, reflecting that at higher molybdenum content, there is a greater alternating ordering between iron and molybdenum cations, thus obtaining a greater magnetic response. The study of anti-side effects is presented in figure 4. It is seen that as a content of anti-side effects increases, the saturation magnetization decreases. In the same way, the saturation magnetization measured in this work is compared with the one reported by Park et al., finding a similar trend. However, they reported a phase transition from tetragonal to orthorhombic for X greater than 0.6, and we identify a transition from tetragonal I4M to I4MCM for X greater than 0.7. On the other hand, it was found that the molybdenum 5+, 6+ ratio increases as the niobium content increases, and therefore the magnetic moment decreases. In summary, in this work, the crystal structure, electrical and magnetic properties of the perovskite strontium iron molybdenum 1-X niobium X oxygen 6 were studied. A structural phase transition was identified for X greater than 0.7, going from tetragonal I4M to I4MCM due to the disorder introduced by niobium at the molybdenum sites. This impacts the electronic and magnetic properties such that the mixed valence of molybdenum 5+, 6+ tends to be mostly 5+ as the niobium content increases. Similarly, the charge carriers decreases in the valence band, suggesting a transition from conductor to semiconductor as the niobium content increases. Finally, the magnetic measurements show a lower saturation magnetization as the niobium content increases, thus indicating the modulation of the properties from ferromagnetic conductor to antiferromagnetic semiconductor or spin glass. Thank you everyone for your time. You can find more detailed information in this website, this one. or in the poster session next Monday at the IMRC 2025.